Hello students, so here we are with the lecture 10 of haloalkanes and haloarenes. So in the previous slide we did the reaction of haloalkanes. Now we have reaction of haloarenes. The first reaction is reaction of haloarene with metals. So reaction of haloarene with metals are of two types, Wurtz-Fittig reaction and the Fittig reaction. In the Wurtz-Fittig reaction, the aryl halide and alkyl halide are treated with sodium in the presence of dry ether, and it gives alkyl benzene. Okay, so if I take bromobenzene and I react it with methyl bromide treated with sodium in the presence of dry ether, what do I get here? Toluene plus sodium bromide. Okay, so the reaction is similar as Wurtz reaction, but the only difference is that instead of taking only alkyl halide, here we are taking aryl halide and alkyl halide. Okay, and then reacting it with sodium in the presence of dry ether, and we get the toluene or the alkyl benzene or the substituted aromatic compound. Clear? Then Fittig reaction. Fittig reaction, what do you do here? Only aryl halide takes part in the reaction. Reaction is similar. So when aryl halide is treated with sodium in the presence of dry ether, we get biphenyl. Okay, we get biphenyl, and sodium chloride is given out as a side product. Clear? So when only aromatic halide, aryl halide, is reacted with sodium in the presence of dry ether, you get biphenyl. Right? Clear? Nucleophilic substitution reaction of haloarenes. So the low reactivity of the aryl halides towards nucleophilic substitution reaction is mainly because of two reasons: resonance effect and sp2 hybrid state of carbon. So here you see the chlorobenzene, the chlorine contains lone pairs and there is a benzene ring here. So because of the chlorine, high electronegativity of chlorine, there is a minus I effect existing here. So the electrons are pulled towards chlorine. But then because chlorine is attached to the aromatic ring, there is plus R effect. So these lone pair electrons are moving towards the ring. So there is a conjugation between these lone pairs and the pi electrons. So here when these electrons move here to the bond, there is a double bond created, and to balance the valency of carbon, this bond breaks and the pi electron comes on the ortho position. So this way, then this negative charge comes on these two carbons here, and to balance the valency of carbon, again this pi electron comes on the para position. Then again this pi electrons of para position goes here on this bond, forms this bond, and this pi electrons, they come on the ortho position here. So there is a delocalization of pi electrons. Okay, and then these negative electrons, this double bond again goes to balance the positive charge that was created on the chlorine because of the delocalization, and this positive charge is nullified and the lone pair comes back on the chlorine. So fifth structure that you get is opposite of the first structure. Here you see the bonds on different position, while here they are bonds on the alternate position. Okay, so resonance structure second, third and fourth shows a double bond character between the carbon chlorine bond. So thus carbon chlorine bond in chlorobenzene is 169 picometers and is stronger and shorter than the carbon chlorine bond in the chloroalkane, which is 178 picometer. So that is why it does not break easily. Okay, so then if you consider this chlorobenzene self-ionization, phenyl cation is formed and the chloride ion is formed. This phenyl cation produced due to self-ionization of haloarene is not stabilized by resonance. Okay, it is not stabilized by resonance. So because it is not stabilized by resonance, it is not stable. That is why the formation of it is less susceptible. Then backside attack. Then backside attack of nucleophile. Now, secondly, when the bond is going to be formed, it can be formed by the backside attack of the nucleophile as it happens in the SN2. So, but when the nucleophile approaches from the backside, there is an aromatic ring here where there are pi electrons. And nucleophile also carries negative charge, so there will be repulsion. So, backside attack is also not possible. So, SN2 reaction is also not possible. SN1 is not possible because the cation, phenyl cation, is not stabilized by resonance, and the SN2 is not possible because backside attack is not possible due to the presence of the aromatic ring. So both of the SN1 and SN2 reactions are difficult. Okay, then how it happens? So nucleophilic substitution reaction, aryl halides are less reactive towards the nucleophilic substitution reaction. What are the reasons? Let's quickly recapitulate. So due to resonance, the carbon halogen bond is getting which character? Partial double bond character. And the molecule is stabilized because of delocalization of electron. Then the phenyl carbocation is unstable because resonance is not possible in it. However, aryl halides, if they contain nitro group, sulfonic group, then they can, like these are electron withdrawing groups. So these attract electron towards themselves. Therefore, the carbon chlorine bond can be, the breaking of carbon chlorine bond can be possible in the presence of these electron withdrawing groups at ortho and para positions. So then in that case, it can undergo nucleophilic substitution reaction. Okay, so in normal conditions, this substitution reaction is not possible. So how will be the substitution reaction here? Let's see. This is chlorobenzene. When it is reacted with NaOH at 623 Kelvin and 300 atmosphere pressure, followed by the hydrolysis in the presence of H plus ions, phenol is formed. Okay, so this NaOH provides what? OH nucleophile, and ONA is formed first, sodium phenoxide is formed, and this on reaction with H plus gives you phenol. Okay, so this reaction is a nucleophilic substitution reaction because here the carbon chlorine bond between the carbon of the aromatic ring and chlorine breaks and it is getting substituted by the OH provided by NaOH. But here you see the temperature and pressure conditions are very high. So what is the other idea that was given was that if there are electron withdrawing groups like nitro group and sulfonic acid group present at ortho and para position, this breaking of carbon chlorine can be possible and a substitution, nucleophilic substitution reaction can be possible. Here you see when there is one nitro group present on the para position, the reaction is happening at 433 Kelvin. While it was shown that without the presence of this nitro group, it was happening at a quite higher condition, more than 600 Kelvins. But then if we put one more nitro group here on the ortho position, then you see the temperature has still decreased. It's come down to 403 Kelvin. And if three nitro groups are present on the ortho and para position, then the possibility of the reaction becomes all the more possible, and the reaction happens on with the presence of water and warmth. So the presence of electron withdrawing group at ortho and para position increases the reactivity of haloarenes. So greater the number of these withdrawing groups at ortho and para position, greater is the reactivity. But let me tell you that electron withdrawing group, if it is present at meta position, has practically no effect on the reactivity. Okay. Now let's see how nitro group is increasing the reactivity. Here when OH nucleophile attacks chlorine, the partial bonds are formed and there is a negative charge created on the ortho position. Okay. Then on the para position and then on the second ortho position. So because of the presence of this nitro group, the pi electrons, they move along the ring. Chlorine OH bonds, partial bonds are formed, and then after finally this chloride leaves and OH bond becomes OH bond is formed. Okay, so that's how this is a reaction that happens because of the delocalization of electron, because of the plus R effect in the ring, and because of the presence of the nitro group, the electron density on ortho and para position is increased. And finally, this chlorine leaves and this OH bond is formed completely. So here you see in this ortho and para position, nitro group present at para position with respect to halogen atom. Nitro group at para position extends the conjugation. As a result, intermediate carbon ion is formed, which is stabilized by resonance and which favors the nucleophilic substitution reaction. Okay, now let's come to the electrophilic substitution reaction. In electrophilic substitution reaction, what is happening? Aryl halide undergoes electrophilic substitution reaction slowly as compared to the benzene. Why? Why it goes slowly? Because electrophilic substitution reaction happens on the ring. And because of the presence of the chlorine group, aryl halide contains halo group. So because of the presence of halo group is showing what? Minus I effect. So it pulls the electron towards itself. Plus R effect is also there when chlorine group is or halo group is attached to the ring. So because of the plus R group, the electrons are shifted towards the ring. So plus R effect is shifting the electron towards the ring, but minus I effect is shifting the electrons towards chlorine. So as a result, the electron density is not as much than in the case of other groups like OH group and all. So here the electron density is less because of the presence of chlorine, and the minus I effect, the electrons are pulled towards the chlorine, but because of plus R effect, the electrons are moving towards the ring. So the electron density is increased, of course, on the ortho and para position, but it is not to that extent because of the presence of chlorine. So that is why it reacts slowly as compared to benzene. On benzene, the free electrons are pi electrons are available for the electrophilic substitution reaction much easily because of the absence of the halo group. Then electrophilic group is more likely to attack at ortho and para position because of the more electron density, because of the plus R effect. Now, amongst the ortho and para products, whose possibility is more? The product possibility is more of the para product. Why? Because of the steric hindrance and because of the symmetry. So, formation of ortho product is less feasible because of steric hindrance, and the formation of the para product is more feasible because of the symmetry. Because para products are more symmetrical as compared to the ortho products. Okay. Then in haloarenes, the halogen atom has got the strong electron withdrawing group minus I. This deactivates the ring and the electrophilic substitution reaction occurs slowly. That is what I was trying to explain you here. Okay, clear? So, how is the electrophilic substitution reaction in haloarenes? The haloarenes undergo electrophilic substitution reaction slowly. Why? Because of the presence of the halo group, the minus I effect is there and the ring gets deactivated, the electron density decreases on ortho and para position comparatively, and therefore the substitution reaction is less feasible and it is less reactive towards the electrophilic substitution reaction. Then uh, what products are formed here in the electrophilic substitution reaction? The ortho and para products are formed. So substitution happens at ortho and para position. Which is more stable amongst ortho and para? Para is more stable because of the symmetry, and ortho is less stable because it causes that ortho position is causing the steering hindrance in the molecule. Clear? Then let's see the halogenation reaction. Halogenation reaction is carried out with haloarene with halogen in the presence of the Lewis acid, ferric salts, aluminum chloride. Okay. So this ferric salts or aluminum chloride, these Lewis acids, they generate the electrophile which attacks on the ring and the product is formed. So here you see the required electrophile is what? Cl plus or Br plus, chloronium ion or bromonium ion. So chlorination, when chlorine reacts with AlCl3, this chlorine breaks heterolytically and Cl plus and Cl minus is formed. So Cl plus is generated and Cl minus gives its electron to AlCl3, which is a Lewis acid, and it forms AlCl4 minus. Clear? So this chloronium ion generated attacks the ring and dichlorobenzene is formed. So when chlorobenzene reacts with chlorine in the presence of anhydrous ferric chloride, it forms 1,4-dichlorobenzene and 1,2-dichlorobenzene. 1,4-dichlorobenzene is para-dichlorobenzene and it's a major product, while 1,2-dichlorobenzene is the minor product. Clear? Okay. Let's come to the next substitution reaction, nitration reaction. So in nitration reaction, what happens? Haloarene, when reacted with concentrated nitric acid in the presence of concentrated sulfuric acid, what is generated here? The nucleophile NO2 plus, electrophile NO2 plus is generated. So HONO2 plus H2SO4, bisulfate ion, hydronium ion and nitronium ion is formed. This nitronium ion attacks the ring and the substitution happens at ortho and para position. Okay, so 1-chloro-4-nitrobenzene is formed and 1-chloro-2-nitrobenzene is formed. Which is more Major product, always the para product is the major product. Clear? The reaction with nitric acid happens in the presence of concentrated sulfuric acid and heat. And the next reaction is the sulfonation reaction. Here the reaction happens between haloarine and fumic sulfuric acid. This sulfuric acid provides the electrophile SO3H plus. Okay. Then chlorobenzene, when reacted with H2SO4 and heat, gives you 1-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid. So orthochlorobenzene sulfonic acid and parachlorobenzene sulfonic acid. Right? Clear? Okay. Then lastly, Friedal-Crafts reaction. Friedal-Crafts reaction takes place in the presence of alkyl chloride in the presence of aluminum trichloride as a catalyst. So haloarenes are treated with alkyl chloride in the presence of anhydrous aluminum chloride, which is a catalyst. Okay. Now, which is the electrophile generated here? It is taking place in the presence of Lewis acid. So RCl, when reacted with the Lewis acid, generates R plus and AlCl4 minus is formed. This R plus is the alkynium ion. Okay. It attacks on the ortho and para position. So chlorobenzene, when reacted with methyl chloride in the presence of anhydrous aluminum chloride, gives you 1-chlorotoluene and 4-chlorotoluene. So orthochlorotoluene and parachlorotoluene is formed. Clear? Then Friedal-Crafts alkylation reaction. So when haloarine is treated with acyl chloride in the presence of anhydrous aluminum chloride, the acyl chloride is what? RCOCl plus AlCl3. So what is formed here? RCO plus AlCl4 minus. So acylium ion is formed. This acylium ion attacks on the ortho and para position, and it forms 1-chloroacetophenone or 4-chloroacetophenone is formed. Clear? Okay, thank you.